Hello, everybody. This is Thursday, April 1st. I see that I've got some alumni here. Hello, Adam. You should be finishing your test. I'm curious what your test is. And so, hello. Oh, man, 2 alumni. Lucy's here, too. Hello. Oh, that's nice. Good morning, Kennedy. Good morning, Sam. Thank you. I appreciate you guys saying hi in the chat. It also gives me an idea who's actually showing up to these. Again, I assume your attendance is being taken with your Tiger ID login, but I'm not really sure. Hello, Nikki, Rachel, Alex. Hello, everybody. So what we'll do today is we'll start with some housekeeping, and then I'm pretty pleased. I'm pretty pleased with today's lesson. What we're going to be doing is we're going to be taking modern atomic theory and essentially finishing off the conceptual understanding of it. Alexandra, that's a good question. If you guys have your stoichiometry assessments done, as long as they're shared with me, I will eventually find them. Here, let me click on the PowerPoint here in advance. You can certainly email me. I'm going to try this afternoon to start looking over some of those stoic assessments today. If they are as well organized as the example I shared with you, it should be very easy to look them over. And then I'll start trying to get those graded. I'll give you comments on your document when I look at them. So yeah, if you, oh, look, Daniel too, hello. As long as you share them with me, I can find them. And feel free to email me also. I noticed that I got a lot of emails after I stopped looking yesterday. So if you emailed me yesterday to look them over after like 1 in the afternoon, I missed that. So I apologize. But yeah, let's get those done. I will try to be around this afternoon to be checking that stuff out. Remember that the third quarter is ending. Let's try to get stuff in by tomorrow. Technically, it's due Tuesday, but if we wrap everything up tomorrow, we should be in good shape for getting everything up for Tyler next week. And again, I checked out one of the Flynn Live Labs. I missed yesterday's. If anybody watched yesterday's, let us know how it was in the comments. But again, I think they are really pretty good. And I think it's a nice way for you to spend your time to get a little bit more enrichment. I feel like we aren't doing quite as much as we used to when we were in the classroom. And so that's a nice way to at least virtually enjoy some of these reactions. Oh, we have a lot more people showing up. Hello, Chloe. Hello, Noah. Mayron, hello. Abby, hello. Hello, everybody. So anyway, so that's the housekeeping stuff. So again, email me with any questions. But your grades are pretty much where they need to be, I think. All right, so again, let's wrap up modern atomic theory here. Now, again, this is baked in. There is high-level math baked into all of these problems, and it's high-level math that I have certainly not taken the time to understand myself. We're talking about like linear algebra, like matrix algebra, all of these really weird sort of high-level math stuff. Now, again, if you are advanced in math, I bet you could handle this stuff. There's plenty of online resources for you to trot along with the legends of quantum mechanics and learn some of this stuff for yourself. And feel free to do that. I think it would be a fun way to spend your time to get good at some of the math behind this stuff. I have chosen not to do that. And with that, there is, of course, going to be sort of a lower level understanding of this. So don't get freaked out. As I've said many times, the math is the coding of quantum mechanics. If you don't learn the math, then you can't really understand the program. And that's fine at our level. Don't get freaked out. This is sort of a problem with science, is that people like to talk about these scientific topics like climate change and things like that, and they don't understand the underlying math that went into these ideas. So they're sitting there reading summaries of high-level science and then adding their own 2 cents, which is great, but all they're doing is talking about summaries. They're parroting back a summary without understanding the science underneath it. So if you want to get engaged at a high level, then learn the math. And if you don't, just enjoy the summaries like I do. Anyway, so we're going to start with Louis DeBroglie. Again, people did not like what this guy was doing. When we're going to talk about his thesis, and again, this guy was a Nobel laureate. He said, if that turns out to be true, I am quitting physics. So yeah, again, even the people who were learning about quantum mechanics didn't really like the ramifications of what was going on. So we're going to talk about Louis DeBroglie here. Now in my video, if you watch the video, I do talk about how to derive the actual wavelength of stuff using de Broglie's equation. you guys can definitely handle that. It's not too complex. If you decide to do that, I think you should focus on watching how the units are working out. I think you should notice that Planck's constant, again, even though he didn't like it, it's baked into all of this, so that's kind of fun. So if you want to see how the math works out, you can go to my original video and go through that. I'm not that concerned about that right now. But anyway, so DeBroglie in his doctoral thesis, and as I understand it, he's one of the only people that won a Nobel Prize based off his doctoral thesis, the paper that he wrote to get his doctors. He said that, if light could have the properties of particles, then why can't particles have the properties of light, aka waves? And so, again, if you go back and watch my video, he predicted that there would be a detectable wavelength of something small like an electron. Everything has waves, but if you look at his equation, since mass is on the bottom, as things get bigger, then their wavelengths get smaller and smaller until they'd be undetectable. But if objects were small, like an electron, they could have a detectable wavelength, and that was actually experimentally verified a couple years later by actually J.J. Thomson's son, which is kind of fun, G.P. Thomson. So what DeBroglie did was he said, you know what, it's kind of neat. And again, this is like the classic follow-up experiment. So Einstein said, hey, listen, light can act like a particle. So your follow-up was, hey, maybe light can, matter can act like a wave. Oh, hello, Katie. How are you doing? Yes, I am trying to step up my quality here during the pandemic. I appreciate that. Wow, this is probably more alumni than current students. Well, that's exciting for at least the alumni. So that's what DeBroglie did. DeBroglie realized that electrons could have a wavelength, and this was weird, but experimentally verified. And so notice how quick of a turnaround this was. In 1924, he proposed his doctoral thesis. Just here too. This is now more alumni than students. That's nice. And so just 3 years later, he won a Nobel Prize. And of course, there's a lot of politics to winning Nobel Prizes, but again, you can learn about that later if you want to. Louis DeBroglie, great guy. Now, Louis originally thought that his the wavelength that he was detecting was an actual physical manifestation. And he came up with this whole theory called pilot waves and things like that. Most people now interpret this as a mathematical representation of the probabilities, which again sounds weird, but just roll with it. So there was a probabilistic manner of electrons, which again was seeped in math that we're not going to talk about. So next along came Erwin Schrodinger. Of Schrodinger's cat claim to fame. Schrodinger led an extremely interesting personal life, and that's all I will say. If you are interested in his personal life, that's easy to find. He was definitely a very interesting character when it came to that. He came up with what would be known as Schrodinger's equation, and this is one of the keynote ideas of modern physics. And what he would do is he would come up with a very complex mathematical view of the properties of a quantum particle, wavelength, position, all this stuff. And it would be called a wave function. So you can see a very, I think this is one of the more simple versions of his equation up there. So you can, it went away. Let's see if it stays. There we go. And so you can see Schrodinger's equation up there. Now, again, we're not going to at all get into the math of this, but again, Google it. You'll see it gets pretty crazy. But the importance is that he came up with a much more mathematically rigorous view of the atom. And it agreed with Bohr's ideas. Remember, we talked about Bohr last time. Bohr said that electrons could only exist at certain discrete distances, right? And those distances were defined by the energy it takes to jump between them. But Bohr struggled to explain anything beyond hydrogen's atom. Schrodinger's view had no such problems. All right, and so Schrodinger's view of the electron became very, very adopted, and he would go on to share a Nobel Prize with another very interesting character, Paul Dirac, in 1933. And again, there's a lot of interesting politics about who gets Nobel Prizes and when they get them, but Schrodinger came up with really sort of the matrix of the electron. Like, what is the coding of where electrons live? And we have essentially completely abandoned any attempt to visualize electrons anymore. So when you think of the planetary model and little electrons orbiting around a nucleus, that has been completely abandoned. And we now have this very mathematical idea of where electrons live based on their quantum properties. So that's Schrodinger. And so one of the ramifications of this was the idea that electrons had sort of the properties now of what were called standing waves. And I've got links to tons of stuff in the description, right? I've got like a dozen really good enrichment links for you. If you want to dig a little deeper, they've been pre-vetted for you. And one of the concepts is these wave functions essentially set up what are called standing waves. And you've all made a standing wave. All of you have played outside at some point and shaken a rope or a slinky. And you can set up that wave so that it looks like the wave is going up and down and not moving back and forth. That's the wave going and falling back on itself and creating constructive interference. And so you get this thing called a standing wave. And there's plenty of videos if you've never played with a slinky before. And so the idea of standing waves is that was very important to this, because what Schrodinger essentially sort of realized with his math, and again, I apologize, if you really understand this stuff and I'm butchering it, feel free to correct me in the comments. But again, this is my non-mathematical interpretation of quantum mechanics. But this was the reason why electrons could only exist at certain orbitals, right? So Bohr said, listen, electrons can't exist here or here because they can't have the right energy. And Schrodinger said, well, that energy was based on the fact that electrons could have this wave-like property, and these waves could only exist at like distances where they could set up standing waves. And so you'll see these two drawings here. And again, this is an oversimplification, but notice that this wave does not fall back on itself. So this wave cannot exist at this circumference. But if you change the circumference a little bit, you can get a standing wave which falls back on itself. And so this is why the electrons could only exist at certain distances and must retain energy to jump between these distances. Because Schrodinger realized that these complex wave functions set up these like wave standing waves, which was really pretty cool. So Bohr predicted different distances were needed to obtain these energies, and then Schrodinger came along and then interpreted this as sort of a mathematical standing wave of allowed distances. And so it's kind of neat. Again, all of this is backed up by math, which you can totally look at yourself. But for those of you who are willing to accept the simplification, this again goes on and on, where Bohr said you could only exist at certain distances. And DeBroglie said, yeah, and electrons have a wavelength. And then Schrodinger said, yeah, and those wavelengths are standing waves, and that defines the distances. So all this stuff was building on each other. Now, these wave functions are very complex, right? And so if you look at a standing wave on a rope, that's great, that's a line. But these are three-dimensional standing waves. And so you can start to see it sets up these really interesting sort of probability patterns in space. And so these wave functions are extremely complex, but the math ends up creating these. If you want to get a slight idea of what a three-dimensional or a two-dimensional standing wave might look like, I would recommend that you check out the works of Physics Girl, which is down in the description. She's got a neat plate that sets up two-dimensional standing waves, and then she even shows you a three-dimensional standing wave too. So again, all this gets super complex, but you know what? If we keep it simple, we can understand it, at least at a simple level. Now, Max Born is a bonus wise man that I've added to this. I've talked about him in the past. I thought I'd bring him back. He's not part of my original video, but anyway, what Max Born did was he took the work of Schrodinger and essentially like kind of squared the wave function and created a probability field. And so what this would help do is create a really, again, sort of a probability field where you could find electrons. And again, this doesn't sound like much to you, but whenever you see pictures of orbitals, which we're going to be seeing soon, a lot of that was borne out by the little play on words, by the work of Max Born. So pretty neat stuff. Again, I just wanted to mention him. He definitely gets overlooked a lot, but he was very cool too. And so what we end up with are these things called orbitals. All right. And so what orbitals are ended up being these mathematical functions that describe where electrons would be. And so this was kind of the work of Max Born here, that you ended up with these things. And I think I talk about these in the video as sort of a bee captured in a strobe light. And so what we've done in science is this is a little complex. Where exactly could electrons be? And so what you will see whenever people talk about orbitals, which is where electrons can live, they make an arbitrary decision that we are going to make a cutoff at the 90% point. All right. And so what we have are regions of space where you're likely to find the electron. And that's why they have these hard shells. Oops. And so whenever you see orbitals, and we'll talk about these tomorrow with quantum numbers, they look like these hard shapes. Don't worry about these shapes per se. They are simplifications of the complex nature of the world. And so that's what an orbital is essentially where you have a 90% probability of finding an electron at any given time. Now, again, I guess we have to bring up Schrodinger's cat. Schrodinger really did not like all the probability that was getting baked into quantum mechanics. In fact, to show sort of the absurdity of this, he came up with a famous thought experiment called Schrodinger's cat. And so you can look that up and check it out. It was sort of to show how absurd some of the probabilistic ideas of quantum mechanics is. Essentially, there was a cat in a box. And again, it also showed how absurd this was to try to take any of these ideas and put them at a macroscopic scale. So the idea of a cat in a box is not quantum mechanics. It's macroscopic stuff. But anyway, if there was something deadly in the box, we don't know if the cat had died or not until we open the box, and so the cat is both alive and dead. Anyway, he was trying to show some of the absurdities of a probabilistic view of quantum mechanics. So check it out if you want. But it's certainly Schrodinger's cat has certainly gotten its way into our popular zeitgeist. So let's talk a little bit about Heisenberg. No, not that Heisenberg, you Breaking Bad fans. This Heisenberg right here. Well, Adam, that's the whole point. Schrodinger hated cats. Yes, that was the take-home point of Schrodinger's cat. Now, that was the whole idea, is that you wouldn't know if the cat was alive or dead until you open the box. And so the cat had this duality of existence. Again, I'm oversimplifying it, but yeah. I don't think he had a cat. I don't know. He doesn't seem like a cat guy to me. So Heisenberg, the last person we're going to talk about in our blitz through modern atomic theory. And again, I'm just hitting like the top of the fold, dinner party conversation of these people. Werner Heisenberg would, also a great mathematician, came up with a completely different mathematical way using like matrices to determine where electrons lived, worked with Born, worked with Schrodinger, worked with all these other people. Anyway, he would come up with sort of this uncertainty principle. And this would become, again, one of those things that really bled out into pop culture. And so the idea of the very act of observing disturbs the system, and you get all these things. Yes, but that really wasn't what Heisenberg was saying. Heisenberg was defending the idea that there was a probabilistic view of quantum mechanics. What started happening in science is that there ended up being, and there still is to this day, different camps, different camps of why all this stuff was happening. And we had people that wanted to go back to classical physics and people that wanted to think about this probabilistic kind of ideas. And so people were arguing about interpretations, and they still do to this day. And Heisenberg said, listen, all of the criticism of probabilities isn't because we have an incomplete understanding of the system, which is what things like Einstein said. He said, listen, all these probabilities are based on the fact that we don't really understand what's going on. And Heisenberg said, no. Heisenberg said that there was uncertainty baked into the system. It was unavoidable, that you couldn't, based on the math, know things like momentum and position at the same time. It wasn't a fault in our math. It was just a limit of the system itself. And that would become known as the Heisenberg uncertainty principle. And it was in a defense of a certain view of quantum mechanics. And this would be kind of central to what was called the Copenhagen interpretation. If you become at all interested in quantum mechanics, one of the big camps that is still around today is the Copenhagen interpretation. And people like Bohr and Heisenberg was in this camp, and other people were in other camps. And so this was kind of a neat idea. That's where the Heisenberg uncertainty principle came from. Again, as I pointed out in the video, this can be interpreted as the Heisenberg homework uncertainty principle. If you were unable to turn in a homework assignment, you can say, due to Heisenberg's uncertainty principle, I have so certainly determined the momentum of my homework that I am no longer certain of its position in the universe. And that should buy you enough time to run and hide before your teacher gets to you. So that's it. Like I said, don't worry about this. Modern atomic theory is weird. I have done a gross oversimplification of some of the ideas. Again, one of my favorite physicists, Richard Feynman, stated that the more strangely nature behaves, the harder it is to make a model that explains even the simplest ideas. And so really, theoretical physicists have given up on that. One of the big ideas of quantum mechanics is the idea of shut up and calculate. We don't have to explain quantum mechanics. We've got the math. Let's just run with it. So we're just about done for today. What I thought I'd do is just kind of summarize what we know about electrons, going from this point forward. Again, even electrons are weird things. Electrons have properties that act like a wave, right? And so again, when you think of an electron as a ball with an E- on it, you're not getting it right. Yes, electrons can act like waves. They have a standing wave based on the probabilities, right? Just like a slinky and stuff like that, right? Higher energy states require that the electron has different energy and therefore exhibit different frequencies like a wave, right? And again, this probabilistic location of electrons is based on wave functions. So yes, electrons have the properties of waves, but electrons, again, like any other quantum particle, can have wave-like properties and particle-like properties. The number of electrons in the atom is always an integer, right? We always have whole numbers of electrons, all right? That's a particle-like property, right? These particles jump in between orbitals like any other particle would. Right, these electrons do actually travel from orbital to orbital. They don't teleport. If you read high-level physics, like they say, no, that's wrong. They take nanoseconds, but they do actually physically transport. And so there's these particles with wave-like properties that jump between orbitals, but like a particle. And single photon, not a single photo. Sorry about that typo. Let's correct that. Sorry about that. Single photons excite single electrons, right? And these are all kind of things that you would expect from particles. So yeah, electrons are weird, just like light itself, just like photons, right? They have these particles or waves and particles, and so do electrons. And so again, when you start thinking about this, you have to say, you know what, I don't really even understand what an electron looks like. And so you got to let a lot of this stuff go, just let it go, soak in it, enjoy it. You will find it an intriguing companion, as Richard Feynman said. All right. Oh, and by the way, and all electrons have the same charge too. All right, so what are we going to do next time? Next time we are probably going to talk about quantum numbers. Probably. I might shift gears. It is Friday. Yesterday's Kahoot review was a big hit. So plan for quantum numbers for tomorrow. But we might end up pushing some stuff back. Spring break is coming. Woo! Spring break, yeah. And so I might end up shifting things around just a little bit because we only have 2 days next week before we go on spring break. So we'll see. Plan for quantum numbers tomorrow, but who knows what might happen. All right. Oh, yes, that's a good point. I think Lucy is correct. I think she was involved. Yeah, you get to see a 360 video about quantum numbers, I think. Will I live stream Seiko Hanabi? That's a great question, Adam. I may or may not, before the quarantine, have smuggled out some equipment to continue my Seiko Hanabi studies. I cannot confirm or deny that. I have not gotten to that yet, but I might. We'll see. I'm actually going to try to work on a home studio here. I'm going to try to create some place that I can do live recordings that doesn't look like I'm recording in front of, in the corner of my basement. So I might do some Seiko Hanabi. It's on my list of things to get around to if we're here for a while. All right, anyway, so listen. Oh, yeah, one more thing before I forgot. I want to show you the greatest picture ever done. I've talked about this if you're an alumni. This is the 1927 Solvay conference. Holy cow, like this picture terrifies me. There is this, look at all the people that got together to talk about science. There were lots of Solvay conferences. This was the legendary one. I will probably do a video someday about this. I mean, look at all these all-stars. Here are the people that you guys know about. Look, here's Schrodinger, right? Schrodinger's there, right? Who else we got? Wolfgang Pauli, we're going to talk about later. Look, here's Heisenberg, right? We talked about him. Look, here's Niels Bohr, right? Max Born is right here. Look, here's DeBroglie hanging out. Compton, we talked about him. Dirac, we talked about him. Who else do we got here that we actually talked about? Here's Planck, right? AKA Hildy right there. Look, we have Einstein. I don't know who this guy is right here. Look, Marie Curie, we didn't talk about her, but she was there too. Holy cow. Like, man, like look at all these poor people that like missed it. Oh man, can you imagine missing this photo? Like you go out to get lunch for everybody and they take a picture without you. Oh, like this picture terrifies me. You can imagine if someone like Carriage came along and like just ran into them or something like that. Like, yeah, this picture has so many important people in it. And again, that's not even talking about the people I didn't circle. Anyway, I love that picture, man. All right, so here we go. Terrible art improv. You knew it was coming. All right, let's go. Let's go. Oh, yes, true, Hunter. We have heard about. Yeah, man, that 1927 picture. Woo-wee. All right, here we go. I'll take the first two improvs. Here we go. Here we go. Bugs Bunny? I don't know. All right. A castle. All right, I can do that. I can do that. I can do that. I should be in there. I will draw myself in there. All right, Bugs Bunny. That's a. All right, so let's see. Bugs Bunny. Oh, that's tough. I don't really know what Bugs Bunny looks like. Bugs Bunny. It's probably gonna look like Trix the Rabbit. I don't really know. That's a tough thing when you try to draw real characters and you don't really know what they're. This is gonna be the Trix Bunny. I think this is the Trix Bunny here. Nope, that doesn't even look like the Trix Bunny. I don't even. Oh, nope. This is not Bugs Bunny. I think he had gloves. All cartoon characters have gloves. Nope. That's not Bugs Bunny. Nope, that's a terrifying dream state of Bugs Bunny. I don't. Nope. I think he had teeth, right? There's Bugs Bunny. Let that haunt your dreams, right? And a castle, though. I can draw a castle in the background. So here's. I think there actually was a video game called Bugs Bunny's Castle. I think. I feel like that was an actual castle. I used to draw a lot of castles as a kid. Great way to spend some time eat before or after pandemics, right? We got some cupolas up there. Draw some little towers up there. You can do cross sections, and have stuff in there and stuff. And then you can have your perspective of the gate coming down. Look, there's Bugs Bunny. There we go. And inside there is a cat. Is it alive or dead? We don't know. Anyway, so there we go. Plan for quantum numbers tomorrow. Alumni, thanks for showing up. Wow, that was a treat. Yeah, we'll see if we can get more alumni in here than current students. Current students, you should be working on that stoic problem for tomorrow. Again, plenty of help out there. I'll try to get in the chat this afternoon. Check out the Flynn Live Lab. I think it looks pretty cool. I'll try to be watching it this afternoon too. Hey, listen, I enjoyed seeing you in the chat. Please stay safe. You are missed. And thanks for watching. Keep sharing the videos. And have a great day.